Okay, well, right here is where we left off on the last story. We were kind of working through this crazy derivation dealing with multiplication and convolution. And as soon as you take a look at what you've done, you see I'm making mistakes here. So I had some summations being added up here. And I have e to the minus j 2 pi m, a minus times the L factor, and then a plus times the n. I think I got this sign here wrong and this sign here wrong, so we want to make sure we fix that up before we get too carried away. I had manipulated this sum out so that I get everything for the output sequence in terms of the two input sequences. And the key here is working this inside summation. And that one's actually not too bad. You know, if I had if this sum went from 0 to infinity, I'd be jumping all over that. I'd say, hey, this looks like a geometric series. Summation k equals 0 to infinity of alpha to the n, just 1 over 1 minus alpha, right? Okay, but it doesn't go off to infinity. We call this a partial geometric series. And so, you know, if you think about, you know, if I had the summation k equal n to infinity of alpha to the n, I could always rewrite this as alpha to the nth power times the summation k equals 0 to infinity of alpha to the n, right? So alpha to the k, sorry, this should be the kth power. Man, I'm all over the place here today. Okay, so if this sum, so this sum ends up being alpha to the n, capital N, over 1 minus alpha, right? I have alpha to the n times the geometric series. And what I have up here is really this subtraction of this. It's this result minus this one. So kind of the partial geometric series result ends up being summation k going from 0 just to n minus 1 is just 1 minus alpha to the n over 1 minus alpha. Okay? Let me rewrite it again. Okay? I'll try again here. Summation k equals 0 to n minus 1 of alpha to the kth power has to just add up to be 1 minus alpha in the denominator, 1 minus alpha to the n in the numerator. Okay, and this is what we call a partial geometric series. Okay, and the truth is, this thing, you know, the geometric series, we usually worry about convergence. Alpha has to have magnitude less than 1. This one, it doesn't matter what alpha is. It's a finite sum. It doesn't ever not converge, right? And this result ends up being true regardless of whether alpha is less than 1 or has magnitude less than 1 or magnitude above 1. And the easy way to show it is you just multiply it out, right? You take the 1 minus alpha times the sum. Every single term cancels out except for the constant term and the nth power term, right? So it's actually not a hard thing to verify that it works. So this is my partial geometric series. And this is exactly the series that we end up with here. We have a finite sum of something to the kth power, and there should be a factor of k out here. And the k is coming from the term I wrote down incorrectly up there. Oh man. Okay, so there's the kth power multiplied by all of this stuff. If I sum up anything to the kth power, I end up with an expression that looks like this. Okay? Now, the only case here that this doesn't work for is when alpha is equal to 1. When alpha is equal to 1, this expression doesn't make any sense. I have 0 over 0. But that case is really pretty easy to deal with. And the case, and what happens in that case is alpha is equal to 1, so I just end up summing up n values where alpha is all equal to 1. I just end up with a value of n out, right? So my answer here ends up being n for alpha equal to 1, right? Okay, well, let's go ahead and plug that in. And if I plug that in, what I end up with for just that summation is going to be all of this stuff. So my summation, so k equals 0 to n minus 1 of this e to the minus j 2 pi m plus L minus n all times k. When I add those up, I end up with this stuff, 1 minus that stuff to the nth power in the numerator, and then 1 minus alpha in the denominator. So I end up with a ratio of values here. And my numerator is 1 minus e to the minus j 2 pi m plus l minus n times n, right? And then my denominator is just 1 minus this stuff without the n in there, right? Okay. Now, what we run into in this derivation real quick is, look at my numerator here. I have 1 minus e to something where this is always going to be an integer, right? And if that's an integer, e to the j 2 pi times any integer is going to be 1. So what I get out of my sum here is 0, right? Okay. My denominator, I don't care what it is, my numerator is always going to be 0, right? And so that's kind of a troubling fact because, you know, here we are, we derived the value of my output sequence that I'm going to get when I do an inverse transform, multiply in the frequency domain, do an inverse transform. Here's what my output sequence is going to be. And what we just showed was everything in this summation out here ends up adding up to be 0, right? Well, that's not quite the way it works out. It can't be the way it works out. I'm not going to get 0 out of my inverse transform. And the key is there's one case here where that summation doesn't end up being equal to 0. And the case that it doesn't end up being equal to 0 is the case where my alpha value is equal to 1, right? And so what we end up with is this summation here is equal to 0 almost always. The only exception is when this term is where I'm taking 1 to the kth power, and in that case my answer ends up being cap n, right? And the case that matters here is where n is equal to m plus l, right? Okay, so in that one case, I end up with a meaningful result out. And what it means is, when I look back at this summation I'm trying to manipulate, in this term, the term I have my brackets under, almost every one of those vanishes. Almost every one goes away, right? The only ones that live are the ones where that exponent adds up to be 0, right? And those are the cases in this double sum out here that end up living. And then in the ones that live, this value has a value of n if, right, m plus l minus n is 0, right? Okay, and it's equal to 0 elsewhere, right? Okay, so there's kind of what I boiled all that down to. And so, crazy result out. Let me kind of get both of these on the screen for you. My crazy result out is that I end up with my x3 of n is, let's see, I have 1 over n. Oh, no, 1 over n is going to drop out with this 1 over n. I'm going to forget about that 1 over that n term, right? They're going to cancel out. I have a summation over values of m, 0 to n minus 1. And in the second summation over values of L, almost every term ends up being 0, right? The only ones that don't end up being 0 are the values of L that are equal to what? It's going to be n minus m. So here I'm going to have, I have x1 of m, and then I'm going to multiply that by x2, but I'm not going to take every single value of L. I'm just going to write down the one that lives, right? And so this ends up being n minus m, right? Or n minus m, right? Okay, that's what we came up with here. And there's a result that looks a lot like convolution. It's convolving over one period, right? Okay, and this part here, I got to be a little worried about, right? And the reason is, what I got to worry about up here, where this thing drops out, I said, okay, well, if that's equal to 0, I get n out. And the truth is, I have a lot of indexes that are all going between 0 and n minus 1, and it's possible this thing ends up being any multiple of n. Ends up being e to the j 2 pi times an integer, and that would still be alpha equal to 1, right? And so the truth is, I want to look at this, but when I sample a value here, I want to take this index modulo capital N, right? And in your book, they use a little notation where they put extra parentheses and they put a subscript down here for how the index is taken. And basically what it says is, you're going to do a convolution, but the thing you're going to convolve is the periodic extension of x2 of t of n. Remember, when we form these transforms, these things are just finite blocks of samples. And it's real possible when I do this calculation for a given index and the output that this difference ends up being a negative value or ends up being a value that's bigger than n, right? So any one of those things can happen. And if that happens, what we got to look at in terms of x2 is the periodic extension of the original waveform. So here's the kind of the punchline out of that answer. We say this is convolution, sort of, right? Okay, and the difference is we're going to use the periodic extension of x1 of n and x2 of n, okay, because I remember I only have cap n sample blocks. I'm just going to act like they're periodic because I've sampled in the frequency domain. And the other side of this is sum over just one period. Okay, so we're used to thinking of convolutions where the summation is going minus infinity to infinity. Well, now that doesn't make any sense. These are both periodic functions. Once I'm dealing with samples in the frequency domain, I'm going to sum those values over a single period of the waveform. All of that stuff together, we do it often enough, we're going to call it circular convolution. Okay, so circular convolution. So, you know, the punchline there is that the waveforms you're convolving are actually the periodic extension. Let me rewrite the formula here and just show you the notation. So I'm going to say that x1 of